I'm here to represent my team Tech for Impact. Sanitation workers of Solapur Municipal Corporation perform critical operations inside confined manholes and sewer systems under extremely hazardous conditions. These environments contain toxic gases like hydrogen sulfide, methane, and carbon monoxide, along with oxygen deficiency, flood risk, and structural instability. Currently, most operations rely on manual entry without real time monitoring, exposing workers to life threatening risks such as suffocation, collapse, and gas poisoning. There is no continuous visibility for supervisors, no structured safety assessment before entry, and no immediate emergency response mechanism. This leads to preventable accidents, health hazards, and loss of life. Therefore, there is a critical need for a technology driven, real time safety and assistance system to ensure worker protection, reduce manual exposure, and improve operational safety.
System is designed by clearly mapping objectives with corresponding functions while operating with real world constraints. Firstly, the objective of preventing unsafe manual entry is achieved through the pre entry safety assessment function, where multi level gas sensing and threshold based evaluation classify conditions as safe, caution, or block. This directly ensures that no worker enters a hazardous environment. Secondly, the objective of continuous worker safety monitoring is mapped to functions like real time environmental sensing and variable based worker monitoring, which track toxic gases, oxygen levels, and worker health parameters continuously. The objective of minimizing exposure and predicting risks is implemented through exposure tracking and predictive analytics functions, where exposure is calculated as time multiplied by concentration and early warnings are generated for gas spikes, flood risks, and structural instability. For rapid emergency response, the system uses intelligent alert and emergency modules which detect abnormal conditions such as panic signals, gas threshold breaches, or faults and trigger alerts within seconds to both workers and supervisors. These functions operate under strict constraints such as real time response within 3 to 5 seconds, operation in confined spaces up to 9 meters depth, limited connectivity conditions, and safety thresholds like oxygen levels above 19.5% and H2S below 10 ppm. Additionally, system level constraints like 95% uptime, portable deployment, and low latency processing ensure that the system is practical, reliable, and deployable in real municipal environments. Thus, our system tightly integrates objectives, functions, and constraints to build a real time and scalable industry safety system.
Our system is designed as a real-time, multi-layer safety architecture to protect sanitation workers in hazardous manhole environments. At the field level, we have two main components. First, the smart manhole entry node, which performs pre-entry safety assessment by measuring gas levels, water level, and structural vibration. Second, the worker wearable system, which monitors the worker's health, motion, and breathing zone conditions and includes a panic button for emergencies. All this data is transmitted through the communication layer using technologies like BLE, Wi-Fi, or LoRa, depending on the connectivity availability. This data is received by the edge gateway, which acts as a local processing unit. It filters and processes data in real time, ensuring low latency even in poor network conditions. The processed data is then sent to the real-time safety monitoring engine, which is the core of the system. It continuously analyzes gas levels, worker health, and environmental risks and classifies the situation as safe, caution, or block. It also tracks exposure over time and triggers alerts when thresholds are exceeded. In case of any abnormal condition, the emergency escalation system is activated. This sends alerts to the worker through the wearable devices and to the supervisor and control center to the dashboard through the dashboard. So all the system data, including logs, alerts, and exposure history, is stored in the cloud backend, enabling monitoring, reporting, and scalability. Additionally, the system supports AI-based predictive analytics to identify risks such as gas spikes, flood conditions, and structural instability before they become critical. Finally, all the information is visualized in the monitoring dashboard, providing real-time insights, alerts, and control capabilities to the supervisors. Overall, the system flow is sensors, communication, edge processing, decision engine, alerts, dash, and the dashboard ensuring fast, reliable, and life-saving decision making.
Hello everyone, welcome to the demonstration of real-time monitoring safety sanitation system built to keep up the life and dignity of sanitation workers of Solapur Municipal Corporation. Before we dive into the live dashboards, I want to briefly explain how data flows through our system. In a real world deployment under the municipality, sanitation workers will wear physical IoT devices like smart helmets with gas sensors and vital monitoring bands. Those physical devices would send live telemetry data to our backend using MQTT or WebSockets. However, for the safety and constraints of this hackathon environment, we obviously cannot expose physical sensors to deadly gases like hydrogen sulfide or methane live on stage. Therefore, to protect the system and to perfectly demonstrate our how our system reacts to extreme danger in real time, we have engineered a custom IoT hardware simulator. I want to emphasize our Flutter application and Node.js backend are not just playing a pre-recorded video. The software is running exactly as it would run in production. Our Python simulator acts as a digital twin for 10 simultaneous variable devices. It is generating and transmitting live JSON packets over the network of every 2 seconds, mirroring the exact data structures and frequencies of real hardware. It injects realistic data sets covering various emergency scenarios such as sudden gas spikes, structural faults, and flooding, which allows us to prove that our real time socket.io architecture and ML pipelines and alerting mechanisms are highly commendable.
Samved Safety System is a mobile application which is a real-time smart safety system for sanitation workers. It connects workers, supervisors and admin through live monitoring, decision control and predictive safety. This is our login page and I have pre-created a worker, supervisor and admin. Let me start the demo. I am entering the username worker worker123 login. I am scanning the manhole and requesting the permission to enter from the supervisor. Now I am entering the credentials of the supervisor. Here it is the pre-entry node screen wherein simulated, that is using the Python BLE simulator, the simulated values are appearing here and the AI, that is risk assessment we have done. We have given some set of data values wherein the machine learning algorithm is run and these values are reflected here, and real time also AI prediction will be done. So I am selecting the it is in safe state now. If I want to change it, like for simulation purpose, I mean for demonstration purpose, I am converting into manual state. Here let me change the values. It gets reflected here, that is block. Save. Yeah. For worker 1, it is as it is safe, I am permitting worker 1 to enter the manhole. Here is the live monitoring dashboard wherein the heart rate, SpO2 and from the gas badge the real-time sensing of gases like H2S, CH4, CO, O2 is done. Initially it was for the pre-node which is made up of, which consists of a probe, and at 3 levels we will be embedding the sensors. Those will be fetched, and here after removing the probe from the manhole, based on the values that is safe, caution and block, the supervisor allows worker to enter the manhole. So after entering the manhole, the worker will be provided with the helmet which will be consisting of the accelerometer for fall detection and many other sensors, and even the vital band which will measure the heart rate, SpO2, and helmet will measure the motion, and the gas badge will measure the sensor values around him. So this is a live monitoring mode. Let me go to the worker again. So entry status is approved. So I'll enter. The exposure timer starts here, which will be helpful in deciding whether to send the save worker again the next day or the other day. So exposure tracking is one of the feature that we had proposed. So after the operation, the worker will exit, and even if the worker is allowed to, and if he is able to take the mobile inside the manhole, then he can even press the emergency panic if he suddenly want to escalate from there. So later you can stop the exposure time, exit, session ended. So here is the history, and based on this AI will predict whether the worker is allowed to work the next day or the other day based on the based on the consumption of the gases in the manhole. Yes. Coming to the admin dashboard. So here are the alerts and total active workers and the users. Here admin can add the user and supervisors as I have did here, and let me do it. So worker 07 password, worker 07 worker user created. It will get reflected in a while. Supervisor 07 sup 07 supervisor. I'm creating a new supervisor. Supervisor created. Yes, supervisor 7 created successfully, as well as worker 07 created successfully. So here I can enter the new manhole of the Solapur system. Okay. Add manhole added, and it got reflected here. Yes. Next, assignment. Here we can assign a supervisor to particular manhole and a worker to a particular supervisor. Select supervisor. Here are the list of supervisors. I am going to assign worker 05 to this. Assign. Supervisor assigned to zone, and worker is assigned to the supervisor. Here are the alerts that admin can study based on the developments. So this is our developed Samved safety system, and also named as SAFEHANDS. Thank you.
Technical feasibility, deployment, and innovation. Our system is designed to be highly feasible, scalable, and deployable in real municipal conditions, especially considering the constraints defined in our system. First, from a hardware feasibility perspective, we use low-cost, commercially available sensors such as gas sensors for H2S, CH4, CO, oxygen sensors, and IMU-based vibration sensors. These components are already widely used in industrial safety systems, making our solution practical and cost-effective. Second, the system is designed to operate with real-world environmental constraints such as manhole depths up to 99 meters, high humidity up to 90%, temperature range of 10 degrees Celsius to 45 degrees Celsius. So to ensure durability, the hardware is designed to be water resistant and corrosion resistant, protected using sealed enclosures that is IP rated casing mounted in a portable, easy to deploy structure from a network and communication standpoint. We use a hybrid model, BLE for short range communication that is up to 50 meters, Wi-Fi or LoRa as optional extensions, offline buffering at edge gateway. This ensures the system works even in low or no network conditions, which is critical for the underground environments. From a software and system perspective, our architecture is modular and scalable. Our architecture is modular because edge processing ensures less than 3 seconds decision latency, alerts are generated within 5 seconds, system supports 5 to 10 concurrent operations with 95% uptime. So deployment is also simple, requires no permanent infrastructure, can be installed by a single operator within 10 minutes, works on battery for 4 to 6 hours per session. Finally, from a real world deployment perspective, the system can be integrated into municipal workflows by trained supervisors deploying portable kits per zone, connecting dashboards to the control centers. So, overall, our system is not just a concept, it is fully deployable, scalable, and aligned with real municipal constraints. Coming to the innovation. What makes our solution innovative is not just technology, but how we combine multiple layers into a single safety ecosystem. First, we introduce a pre-entry safety intelligence system which prevents unsafe entry before it even happens. This shifts safety from reactive to proactive. Second, we combine environment plus worker plus structural data, which is usually handled separately. Our system creates a 360-degree safety view, including gas conditions, worker health, flood risk, structural instability, and yes, third, we implement edge intelligence where decisions are made locally instead of waiting for the cloud processing. This ensures instant response in life critical situations. Fourth, we introduce exposure based safety where risk is calculated as concentration into time. So enabling long term safety tracking, not just instant alerts. Fifth, our system supports predictive safety using data patterns to detect gas spikes, flood risk, structural anomalies before they become dangerous. So, unlike existing systems that only detect danger, our system predicts, prevents, and protects, making it a complete smart safety ecosystem.
Coming to the innovation part of our SafeHands system, the first one is AI pre-entry prediction. Instead of waiting for a worker to step into toxic gas, our system predicts the danger before they even go inside. It uses an AI model to analyze the environment and flags potential gas spikes early. This means we actually prevent accidents instead of just reacting to them. The digital handshake. A worker simply cannot enter a hazardous manhole on their own. Our system forces a digital approval from the supervisor only after our AI clears the environment. This completely removes human carelessness and shortcuts from the equation. Third comes the triple tier telemetry sync. The split second a sensor detects danger, it doesn't just beep in the dark. It instantly alerts the worker underground, sends an alarm to the supervisor above the ground, and flashes on the city's administrator screen all in 1 second. Multi-hazard tracking. We don't just look for one type of toxic gas. Our system acts as a complete guardian by simultaneously tracking if a worker has fallen down, if their heart rate is dropping, or if the water level is if the water level is rising too fast. I mean, in the case of flooding. Offline resilience. Manholes are basically concrete bunkers, so losing internet signal is common. If the connection drops, our hardware safely records all the workers' data locally with the help of an edge gateway, which we have already explained using the architecture diagram. and it automatically syncs it right back to the cloud the moment they step above the ground and the internet connection is back.